Good morning, good afternoon. How's everybody doing? My name is Mark Richardson, Marketing Manager with Vibrant Technology, and we welcome you to another MEscope webinar. Today's topic is MEscope for Beginners, Processing Videos Part 2. If you were with us for Part 1, we welcome you back. If you didn't get a chance to view Part 1, you can always go out to our YouTube channel and replay it out there. Today we're going to be talking a little bit about, just to kind of summarize what we're getting into. We're processing a video. We're going to be talking a little bit about aliasing, removing background motion, and then how to perform spectrum averaging to reduce noise. So I'm joined by my brother Sean Richardson and my father Mark Richardson Sr., the CEO and founder of Vibrant. Couple of housekeeping items. We are recording this webinar, so we will get this out to you at the tail end of the, or usually probably tomorrow or next week. We'll get this up on our YouTube channel, so you can go back and review it. If you do have questions today, let's hold off on the questions and we'll get those answered at the tail end of the webinar. You can type your questions into the questions dialog box on the right-hand side of your screen there. When we go to webinar panel. And with that, let me hand things over. Sean's going to start us off today. Sean?
Good morning. Thanks, Mark. Perfect. Thank you. Yeah, as Mark talked about, we got started on this, I don't know, 3 weeks ago, a month ago, or whatever. We went through the first section. More than anything in that, we talk about, thoughts and considerations for how to set up a video, ways to get your video the best quality and to meet the needs that you need for your video within your cell phone, considering your frame rate and how long the video is and everything. And then we talk about the topics for today. So what I want to do is I want to do a really brief recap and just kind of go over the slides again that we did last time. For those of you here, you'll hear it again quickly. For those that weren't, you'll get a really reduced version of what we did before. But we'll go through and just talk about those considerations, and then get into the things that we're talking about today, which again, we're removing background motion from a video, spectrum averaging, and then unwrapping aliased orders. We'll talk about, kind of the whys and the hows of that, and then I'll pass it over to my dad, and he'll get over and we'll actually walk through, performing these tasks on the video itself. So let's jump into a quick recap again of last week, or in the last webinar, I'm sorry. But we talked about different iPhone options, which you can get in there. iPhone specifically, obviously you can use Android or any other phone, but in the iPhone specifically, they have HD mode of 30 and 60 frames per second, 4K mode of 24, 30, and 60 frames per second, and then an HD mode for slow motion, which is 120 and 240 frames per second. Again, if you can get away with having a lower frequency span, the 4K is the best option, usually at 60 FPS, just because the resolution, extremely crisp. In the video there, if you get it, you can look at the one online, but I just kind of flipped through.
Okay.
How to switch there, and then we switch to slow-mo and the tabs on the bottom there. We talked about video considerations, HD versus 4K. Obviously HD gives you 1920 by 1080 pixels, 4K is double that, or 4 times that, I'm sorry. So again, we talked about the resolution. So if you don't need a huge frequency span, you can get much sharper resolution, 4 times to be exact, out of 4K. And the frames per second, what you can get out of it, as far as your frequency span in hertz and RPMs. If you have 30 FPS, you can do up to 900 RPMs, all the way up to 240 FPS, which would be 7,200 RPMs, or 120 hertz if you're sticking with a traditional structure there, a non-rotating and reciprocating machine. How long to take the video for, what kind of resolution you can get. Obviously, if you do a 10-second video, you can get 6 RPMs or 1/10 of a hertz, 20 seconds. It just multiplies out there. So those are the considerations for the frame rates, the length of time that you're going to use. In the phone itself, how we would go through here, the structure alignment, we want to kind of maximize the structure within the window of the phone, or what you can see on there with recordable video. So specifically, if you want to go in there, you're looking at a part of a machine or part of the structure only, you can obviously zoom in on that. But basically everything that you want to see, you want to maximize that, and that'll also give you the best resolution. So whether that means moving closer or further away, zooming in, zooming out, you just want to make sure that you can see it there on the screen. And we recommend using a tripod. You can get them for cheap on Amazon. Some of them come with a Bluetooth remote to start and stop your video. But what the biggest thing, and we'll talk about it today also, with the tripod, is making sure that video is stabilized. I don't use a Bluetooth, just Bluetooth trigger for it. I just start it and then stop it, and I'll clip a couple seconds off the front and back into the video to make sure that any camera jitter from the results of starting the video button is removed. But certainly you can use a Bluetooth trigger for your video. But again, definitely recommend a tripod if at all possible, just to reduce any sort of camera jitter and maximize the stability of your video. And then we also talked about how to get the video ready for export, specifically in iPhones. If you use one of the slow-mo videos, which is your 120 or 240 FPS, it puts I don't know what to call it. It's like a cinematic feature that they have in the phone. So it'll start regular playback and then it'll slow way down in the middle. Well, if you export that video, that slowdown will remain in the video, so you got to take it out first. So essentially what you do is you take the video on your phone, you hit edit. There's a slider bar in the middle, so you can adjust the amount of slow-mo section. I take that slider bar, slide it all the way to the right, save your video, and then you just have a normal playback speed video of 120 or 240 FPS. And again, we went through it last time. It just kind of shows how to do it, but use the slider bar and then sliding over there, and we'll skip that. Today, we talk about removing background motion, and it's kind of a unique feature in videos. Really useful. What I can make it equivalent to, let's say that you are on a structure, you're on a platform that has a lot of vibration that's induced by the machine that's on there. A lot of times you're going to have to take your measurement there. So even if you're using accelerometers in a traditional sense, the only way to really get that motion out, say if we want to focus strictly on the vibration of the machine and not on the vibration of the platform that's included, because obviously the two of those are going to be combined. The only way you could really do that would be by putting a accelerometer on the platform itself, measuring that data as well, and then taking those time waveforms from that accelerometer and removing them from the machine as well, or from the structure as well. This is the equivalent of that. It's really kind of taking a normal, meaning in the video sense, taking pixel or pixels that are stationary, or are the motion that's not related to the structure itself, and then taking that data and removing those time waveform data from the rest of the combined data to, for lack of a better word, to normalize your video. So essentially when to use this, we talked about elevated platforms a lot, paper mills, things of that nature, where you have multi-story machinery and you need to test things that are higher up. Obviously, when you set the camera on the platform, if you're several stories up, that platform is going to be vibrating. So we want to get something in the background that we can select, as we know that it's not moving, or it's moving the same amount as the platform itself. And then we want to select those, and we'll remove that background motion, and it'll take it out of the structure as well. And we'll show how to do that. But another good place to use this, a lot of times people do measurements for generators or engines on ships, oil rigs, same kind of concept. Obviously, it's moving with the ocean, so we want to get something in the horizon, if at all possible, or something within the hull of a ship that is not generator or not engine related. To select those points and then remove the background motion. So we're strictly getting the vibration and the ODS of the structure or the machine itself. And then unstable foundations, all the same concept there. But like we talked about, the way it works, you get in there, you want to select a known stationary point in the video. You can do a single point, you can do several points, you can grab a group of points there. And what we do is you're going to remove that time waveform data that's common to all the points in the video. It'll take that data that's associated from a known stationary point and then remove that data from the actual structure that we want to analyze, just so that we know that we're only getting that structure-borne noise that's directly related to the structure only, not with the peripheral vibration, if you will. Other things we can do. We talked about spectrum averaging. Really the best way to clean up a signal, just using the data that's in there, obviously. We reduce the noise and clean up the spectrum. Obviously easier for resonant peak identification in structures, also specifically for rotating reciprocating machinery, and it cleans it up. So what we can do is we have obviously a number of samples, no different than when we take accelerometer data. You have a set number of samples. We can say the number of averages that we want to do, and so that'll say that'll determine the number of samples per average. Basically slices it up like a pie, and then we'll do overlap processing as well. And we'll show this all in the video when we go through it. But if you look at you're going to look at the FFT data ahead of time, prior to averaging, and you do your spectrum averaging with your overlap processing. You look at after, considerably cleaner, just a much more usable form of data at that point. For a lot of rotating reciprocating machinery guys, you're used to using a Hanning window to reduce liquid leakage and sharpen the peaks within the FFT. Same concept, same availability in videos here, no different than MEscope VES, but obviously that's in there, so you can utilize it the same way and sharpen your peaks up. We talk about in here, you can do a bunch of different analysis. What we'll do on videos typically is we'll do ODS-FRFs, and a lot of people use cross spectrum, but the biggest advantage specifically with videos utilizing ODS-FRFs is that you can integrate and differentiate the data after it. So what will go in there is, obviously videos, the format that you're going to get out of there is displacement, go to velocity and then acceleration. But, to get magnitudes and velocity that a lot of, rotating reciprocating machinery analysts are used to there, ODS-FRFs allows us to get to velocity there. So definitely good use. And we'll cover that in the video as well. The last thing we can do is something that's unique to MEscope, and for anytime you have a rotating reciprocating machinery, you're going to have orders or multiples of the running speed. What we are able to do is basically double the frequency span by doing this. But once we kind of highlight or put a cursor or a band on the running speed there, and this is kind of an over under. If you look at the image to the right, the top is your regular video that would come out of there, and we knew that it's a little trainer that we have, and you'll see in the video here, but the running speed was set at basically 1,000 RPMs, 1,006 or something like that. It may just be a sample off, but basically identify that. Once you identify that, then we can unwrap the aliased order. So then the image at the bottom half of that is unwrapped aliased order. So again, you can see your initial running speed to the left, that's your 1,000 RPMs, and it drops to 2,000 and 3,000, and you can kind of see how that 3,000 peak, that's initially in the aliased orders, it would be to the left of the to the running speed. Now we unwrap it and it lays out the way it should, and it retains the magnitude data with it, and it gives you very simple order peak or multiples identification. So it just lays it out and you work that way. Now there's, if you get to high enough frequency specifically, there's going to be, sidebands that if you unwrap the alias order, you're going to lose the sidebands. It doesn't lose it from the original data, but if we want to look at the unwrapped alias orders, you're going to lose sidebands on those peaks. But for simple, order tracking and maintaining magnitude data and everything else, this is the way to do it and essentially double your usable frequency span. So those are the topics for the day. Like we talked about, I'm going to pass it over to my dad. We're going to kind of walk through these topics here and kind of see the how-to and the resulting effect on the actual video and the playback. So with that, Dad, it's all yours.
Okay. Thanks, Sean.
Let me make you the presenter there. There you go.
Okay, show my screen. Can everyone see my screen?
Yep.
Hopefully. Let me bring up videos. This is a separate program from MEscope VES. So any of you that own MEscope VES, I'm going to cover the whole screen with this here. Let me just go back. Okay, so this is the opening screen of MEscope videos, and it's just for processing videos. And of course, we're focusing on using your cell phone, which everybody has in their pocket, so that you can start doing video recordings. And Sean explained the frequency band and how we can unwrap orders and so forth. So you can do a lot with the camera in your cell phone. And we're going to look at some data here from the rotor kit and look at its vibration. And it was all recorded at 60 frames a second. But those, with an iPhone, those are very accurate video frames. They actually have 8 million pixels in each frame. Now, when you go to the higher sample rates, the number of pixels drops down a bit. And then we also resell a camera. We're just a software company, but we do resell a camera that'll go up into the kilohertz region. So if you're looking at smaller structures that vibrate at higher frequencies, you may need that camera to look at the higher frequencies, or any digital camera. But typically when you sample at much higher frequencies, you need artificial lighting because the pixels just don't gather enough light at a very high sample rate. But in your cell phone, they got special processing in there that will brighten the picture, and you just get wonderful videos to work with. So that's a place you should start. And then use the trial and error method. Just make some videos, bring them into MEscope videos here and work with them, as I'm going to do here in a minute. So I can either open a raw video, or I can open an existing project, MEscope project, and these are called VT Max. You can see there's several of them that this version of the software is pointing to that I've already processed. And so I can open one of them, or if I own a VES package, a modal package, an ODS package, and you add what's called VES 9000, that has very similar video processing capabilities in it to what we're going to look at here in this separate piece of code. We designed this to be usable in the field more as a portable on a laptop or a portable Windows computer, so you can actually use that with your cell phone in the field, in the factory, and look at animated ODS, what we call video ODS. Look at the animated pictures, amplify the vibration, see what's going on. And the advantage of a video is that not only are all the pixels simultaneously sampled, just like in a multi-channel acquisition system with accelerometers, but you're going to see things moving around in a video that you maybe weren't even thinking about on the test article. And when you lay out a modal test or an ODS test with accelerometers, you can use FEA mode shapes, you can do a lot of different things, or the customer just says, hey, I got a problem here with this machine. And so you put a couple of accelerometers on the motor and a couple on the pump and maybe a couple on the gearbox, and you can see what's going on based on that accelerometer data. But with a video, you're going to see everything in the field of view, and you may see things moving that you weren't even thinking about. So that's the advantage of the video. But let me go ahead and open up a raw video and take you through what we call, okay, so it's going to ask me to open up, and I'm going to go, oh boy, I need to go find some videos here. Just let me take a second, and I'm going to go out here into a website. And so here are some videos that are similar to what Sean already showed you in his presentation of a rotating machine that we have here in the office. And I can pick any one of these videos and open it up. Let's just pick one. And you can see they're all labeled 1 inner, 1 outer, 2 inner, 2 outer. Well, these are little screws that we screwed into the rotors of this rotor kit to cause unbalance, just to basically cause it to vibrate more. Now, in a refinery or a power plant, you're going to have thousands of machines like this that, even though you balance them as carefully as you can, they're still going to vibrate. So let's just open up one of these things and take a look at it here. So here it is, and you can see in the still picture, this was the one called four outer. So there's actually 4 screws screwed into this outer rotor that are going to cause this machine to vibrate when I turn it on. Quite a lot of amplification there. So the first step here, I'm just going to work you through, and this is the same in VES. If you order, well, let me say one other thing. If you own VES, and let's say you own video ODS or visual modal, I'm getting my terms mixed up here. If you order the VES 9000, that is the video processing option to VES. So you can do curve fitting and SDM and all the other things you can do in VES. But the way we have it priced is if you order the VES 9000, you also get MEscope videos. You get this separate program. And its wizard is identical to what's in VES. And we have 5 steps here. So let me just take you through these real quickly, and we're going to process this raw video. So the first thing I can do is crop the video. Now, as I said, there's 8 million pixels in each frame of this video, and there's quite a few frames. At 60 frames a second, if I process, let's say 15 seconds in my cell phone, if I record for 15 seconds, that's 900. That's almost 1,000 frames or time waveform samples. What we do with our software is we extract time waveform samples or time waveforms from each frame, and we'll see in a minute here, rather than the 8 million pixels where I could basically get a time waveform from each pixel. And the way we do it is the software just goes frame to frame to frame through let's say the 1,000 frames, and computes a time waveform based on how the pixels move around. That's how all this technology works. But what we do is we use grid points. So I'll show you that in a minute. But in order to cut down the processing, which is really a function of the number of pixels in each frame, and we got 8 million of them here, I'm going to crop the video, and let's just crop it. I'm going to draw up a little box here I'll get a little bit of, and then we'll go back and we'll work with the whole test article when we do some of this other processing. So I'm going to go to the next step, and so this is going to be a much smaller. Now here are the frames. So you can see I've got 967 frames. This is a 16 seconds of data at a recording rate of 60 frames per second. So you just multiply 60 frames per second times 900 frames, and you're going to get 16 seconds of data. So it's just simple math, but we'll go on to the next step. Now we can check frame validity. Sean mentioned if you go to the 120 or 240 frames per second, you need to remove the slow motion frames from the video. Otherwise, you know, you don't have uniform sampling frame to frame to frame. So you want to make sure you have that. And this little down here, the check frame validity, if there's anything in your frames that don't, you know, they're not uniform in sequence and so forth, we check a number of things, but we don't need to go through that. This is a good video. We'll go to the next step. Now, here's what I was talking about. The first step, I cropped it. The second step, it was all set up properly. I can go back here, but we set the number of frames per second. That's basically the sample rate. And then the number of frames, and I can shorten this way down. Let's just do that because that will shorten the processing time considerably, because as I said, so we're only going to have 4 seconds of data here. We'll go back and use the full 16 seconds in a minute, but I just want to take you through this. And if I shorten this down to 281 frames, it's going to process the video a lot faster. So let's go to the next one. Now, this is something unique to MEscope. And of course, any of you that own visual ODS or visual modal, visual SDM, we build a 3D model to look at accelerometer data using points, lines, and surfaces. With the video, we use that same technology, and you can see here that we have points, and then all the points are connected together with quad surfaces, what we call quad surface, you know, just 4 points. So that's behind the scenes, and the video itself is being shown on this quad surface, and now I can pick the number of points. So I want to make sure if I want to look at the vibration at the top of this bearing block here, which is where I would maybe compare answers with an accelerometer that's sitting or, you know, attached to the top of the bearing block. And we've done that with this simple machine, but out in the real world, you got maybe accelerometers attached here, there, and everywhere. You want to make sure that if you want to compare answers, and we've done that, and the videos are just as accurate as an accelerometer. The only limitation being that we only get 2-dimensional motion off of the video, as opposed to the accelerometer, perhaps 3-dimensional. But if I have a uni-XXL, then, you know, vertical versus vertical, I can compare those answers. So for you engineers that are interested in 2 decimal places of accuracy, you can get that from a video. They're very accurate. And you can see here that if I want to pick some points now with a fewer number of points, I've got 2,200 points in this grid here. And I got some points right on the top there that are going to move up and down in the video ODS, and I can compare those answers. So let's just go ahead and now we're going to extract the time waveforms. So I picked the number of points. I've cropped the video down so I'm not using 8 million pixels, but there's still a lot of pixels in here. And we'll see how long it takes here to just process this. This is, again, trial and error. You should try little parts of your video because it will run a lot faster. If I do the whole video, it's going to take like 3 to 4 minutes. Here we'll see it should go a lot faster. What we're going to end up with now is a data block full of time waveforms for 2,275 points. So twice that number because we got vertical and horizontal TWFs. So let's just go ahead and start this. Okay, it's going to take a minute to process this video. Pretty good on my computer. If you've got better graphics hardware in your computer, it's using the NVIDIA chips in my computer that Windows will use to process any graphics. And so we're using those NVIDIA chips in MEscope through the software to process, what do we have, 280 frames of this video, and then crop down. So maybe we got 1,000 pixels, but we got 2,200 75 points. So now what we've got when we look at it here in a second is the time waveforms, and then MEscope will compute the FFT of all those time waveforms. So we'll also have the what we call the digital frequency transform, or the DFT. Now here's where we scale things, because the raw video simply computes displacement, but it's not in engineering units or in physical units. So here's where I set up the physical units. If I click this, and this is like scaling your accelerometer, where you put in the sensitivity, and then if you've got data acquisition hardware, you may have other ways to scale your data so that you get actual engineering units. And as Sean already mentioned, if we compute something like an ODS-FRF, we can integrate and differentiate that data. Well, we can also do it with the time, or with the frequency data and the time data in MEscope. But I'm going to set the distance here. So again, you need to pick kind of a known distance. I'm going to pick, let me just pick something like this. And that's about 3 3/4 inches. I can take a ruler. And even if I can't pick something in the plane of the video that's pretty much in the plane, it doesn't have to be vertical, horizontal, it can be any angle, but I need to know, accurately, what is that? I'm going to just put in a number, 4 3/4 inches, or 1/4, whatever that is. Let's go ahead. Now the data, all the time waveforms are going to be scaled. Now here's the other thing I wanted to show you, and Sean talked about this. This is the first way to remove background motion, anything in the video frames. You may have some guy walking behind the machine while you're taking data. You may have a bird flying through. You have other things in the video that you're not interested in. Or as you can see here, let me just set this back. This is what we call a magnitude filter. And what it's doing is it's getting the magnitude of all the time waveforms, and from the smallest magnitude to the largest. Well, I'm interested in some of this motion in the middle here. You can see most of the points, and this is just a point count. So I got like almost 1,000 points that got very low magnitude. So if I click that once, I just eliminated them, and look what happened to the picture. All this background, it could be the sky, in this case it's a wall. I don't care about that. I only care about maybe how this bearing block is vibrating, or how the rotor is twisting and distorting. We can get mode shapes off of a video that you couldn't get any other way, but we can actually see the mode shape of the rotors, which is pretty amazing to me. Let me crank it one more time. I'll take out even more data. So you can see it just took everything out up here in the on the wall and down here. I don't care about these points. I only care about the rotor and the bearing block. So now we'll just finish. We're done. You can see that these are the 5 steps. We went through all 5 steps, and I'm going to finish. Okay, so now we got a sweep animation going on here, and you can see a bunch of peaks down here in the data, and the rotor. What's being applied here is that we're putting a frame of the video onto the picture as we sweep through frames of the video. So each sample of time waveform corresponds to a frame of the video. So you can kind of see what the video actually recorded here. Now, if I click down here to the DFTs, now I'm just seeing a sinusoidal amplitude or deformation of, and I can come up here and crank up the amplitude. Let's just crank it up here. This is the real advantage. So now I can see, look at the whole base plate is moving because this thing was just sitting on some rubber mounts. And, you know, the vibration of the bearing block is showing up here more so. But there's more vibration actually, or more amplitude in the rotor itself. And you can see some anomalous motion here of the shaft. But so I can do this. This is the beauty of getting it into MEscope. I can crank the speed, I can crank the amplitude, or I can pause and continue. Number of things I can do here. But let's go back, and I'm going to cancel out of here. Unsaved changes, no. And let's just go back and grab a different project, another VT Max, and this is one that's already been processed with all the data. How are we doing on time, Mark? Is it time to answer some questions? Maybe we should just ask again, if you have any questions in what you've seen so far. Let's handle those.
We don't have any questions right now, but if you got some questions, go ahead and type those in there.
Yeah, go ahead and let's have a good Q&A, because we're presenting a lot of information here. And so here is the same machine. It could be one of the other videos. And you can see that we didn't set a distance. I didn't, during the wizard, when you're supposed to pick a distance in the video between point A and point B, that was not done with this. So it's just showing displacement. So here's the time waveforms up here, and then we're doing a sweep. And each sample of the time waveforms, you can see there's 16 seconds. So this is the full video at 60 frames per second that we recovered, or that we uploaded to MEscope videos from the cell phone. So you can see, you know, the pulley here is moving around quite a bit, and the rotors are moving around a little bit. Again, if I crank up the amplitude, let's just see what this thing looks like. Now in the time domain, it's a little hard to see it, but you can see the cell phone captured good motion down here on the base plate. Now let's click down here into the frequency data, and I'm going to change my cursor over here. Let me see, how do I get to that? Okay, so here it is. I've got the same cursors we have in VES, band cursor, peak cursor. I'm going to set the peak cursor up here on the running speed, 1000 RPM. So the other advantage, and you can do this with accelerometers too, you don't really need a tachometer. You can, the running speed of the machine is going to show up as a large peak in the DFT, in the Fourier spectrum. But you can see the video, the cell phone captured all the motion of the base plate. Now I've exaggerated the motion because these points are moving quite a bit more. But if I'm just interested in, you know, how the bearing blocks are moving, and using that to assess the, you know, compare this week's displacement with last week's, and of course we'd want to have it in the right units. But the other thing I can do up here is, let me see what's going on. I can display the data. Well, I need to scale it, so it's not allowing me to change the cursor. Or maybe it is. Well, let me turn on the orders here. And as Sean already explained to you, it will display orders. Well, we're not seeing it in this. We're not seeing it here, but these are the order peaks of the other orders. So let me just go ahead and show you some of that functionality, which we kind of ended his talk with. I got all kinds of things I can do in here. I can unwrap the aliased orders. So let's do that. we're probably going to need another session to just cover some of these other details. There's just a lot of stuff in here, but it all has to do with videos, and specifically okay, show aliased order. So let's just see that. And oh, it went ahead and did it for me. Let me just separate this. So you can see the 3 order peaks, and these 2 are the aliased orders, and it's unwrapped them down here. So here's 1,000 RPM, which is the running speed of the rotor. And here is the 2 times, and here is 3 times. So many times when you're looking at machinery problems, you want to look at the order peaks. And we can accept those, and then we can go animate at the 3 orders and see, just kind of take a quick look at what the animation looks like at each one of these orders. Okay, so there's the running speed. We had that up before. Well, we're sweeping here. Let's go down here. And so there's the first order, and you can see a very simple mode shape of the outer rotor. The vibration changes, the base plate is not moving nearly as much, and that's at 2 times, and then here's the third order over here at 3. Now you can start to see the mode shapes of these. You see this mode shape here? The 2 sides of the rotor are moving differently with what we normally look for in mode shapes, a deformation. It's a simple waveform like that. And if we go back, let me just change the animation. We'll lower the amplitude a little bit, but we'll be able to see some pretty simple mode shapes of those rotors. So you see a lot of information. Now, the pulley belt is kind of dominating everything. It's moving around, and then this bearing block here has got a lot of motion in it. So, if you're going to show things to the boss, you probably want to get it down to, or the customer, to get it down to something that's a little more realistic. Anyway, next session we'll go into calculating ODS-FRFs and the details of doing that. Let me just show you some of the commands for doing that. Now that's going to take the time waveforms and calculate ODS-FRFs, and it uses spectrum averaging. And we can crank up the number of averages. You can see the overlap processing, 95%. So Sean talked a little bit about that. Windowing, we can use a Hanning window. A rectangular window is basically no window, or a flat top window. And the flat top widens the resonance peaks, but you can't curve fit that data. The peak values are more accurate than a Hanning. But when we do spectrum averaging, and we'll get into aliasing and windowing issues, the Hanning reduces, not aliasing, but leakage. I used the wrong term there. Leakage is the term that happens. The energy leaks out of the peaks, the resonance peaks, if we're looking for mode shapes. And the Hanning window reduces that, so we can actually curve fit ODS-FRFs and get what are called operating mode shapes. So we can do all that. You can see here, again, the background, a lot of the background was removed in the wizard. That's important. And then we need to pick a reference. So this is ODS-FRF. We need to pick a point either in the X or Y, and again, we're going to pick a time waveform as a reference, as opposed to an FRF, where the force is always the reference. Well, it could be the response also. We're getting into signal processing details here. But anyway, Mark, that should wrap it up for this presentation. if we have no questions, I guess we're done.
Yeah, we got no questions, so we appreciate you all attending, and stay tuned for our next one. We'll get another one of these spun up next month, and we'll leave it there, everybody. If you have any questions, feel free to shoot us an email, though. You can always reach out to sales@vivetech.com. Happy to answer any questions you might have after this webinar. If you view another webinar online on the YouTube page, we can answer your questions. With that, we'll let it go, and everybody have a great afternoon, great evening. We'll talk to you next month.
Thank you all for attending.